Hi everybody and welcome to lesson 7.2.1. This is the only lesson in 7.2, or rather the only video in lesson 7.2. Okay, let's get going learning about the Nernst equation. Now, first we're going to talk about electric potential, free energy, and equilibrium and how they are all related. So we're going to compare those first. So if we're looking at the E cell, so if that is greater than 0, if it's positive, that means delta G is going to be negative, which is less than 0, right? Because that's going to be spontaneous. And in that case, K is going to be greater than 1, and we're going to proceed in the forward direction. Now, if E cell is equal to 0, delta G is also equal to 0, K is equal to 1, and at that point we are at equilibrium. We're at equilibrium, okay? And so that is also, of course, our dead battery state at equilibrium. Last one, if E is less than 0, if it's negative, that means it's not going to proceed in the forward direction. It's not thermodynamically favorable, not spontaneous in the forward direction. Delta G is greater than 0, and K is less than 1. If K is less than 1, that means our reaction is going to proceed, but in the reverse direction. Okay, so let's take a look at some of the differences between potential and free energy. So delta G, which is free energy, and E, these have opposite signs. So that means, again, like we said, if delta G is negative, E is going to be positive. If delta G is in joules, and E is in volts, and which is also broken down into joules over coulombs. And delta G depends on stoichiometry, but not E. So by depending on stoichiometry, of course, we're going to figure out that depends on the number of electrons transferred. So at standard state, we have our equation for delta G here. Delta G naught at standard state equals negative NE negative, which is the number of moles transferred. So the negative number of moles transferred. If we have 2 moles of electrons transferred, of course, N will be equal to 2. F is our Faraday's constant, right there, 96,485 coulombs per mole of electrons. And that's where we can see why that depends on the stoichiometry of the reaction. So at the non-standard state, delta G, we have the same equation, but we're just not at standard state here. So you notice you're missing the not symbols. Now we can derive our Nernst equation from a couple equations that we already have. So we learned from lesson 6.3 that delta G equals delta G naught plus RT ln Q, right? And remember that Q is your current equilibrium position. It's not K, it's not at equilibrium, but it has to do with the current concentrations that you have at any moment in the reaction progress. So if we substitute delta G is equal to negative NE FE that we had up here, we are going to get this reaction, this equation, divide both sides by negative NE times F, and we end up getting our Nernst equation. So the Nernst equation is pretty important. This can tell us all about how our concentrations are going to affect our voltage, essentially. Now, the Nernst equation is not on the periodic table. It's not on your periodic table. You do have this equation, however, on your periodic table right here, but the Nernst equation is not. Now, something important to note is you won't be asked to solve problems directly from the Nernst equation, but you'll have to explain conceptually, how one variable will affect another. So it is very advantageous to you to go ahead and just memorize the Nernst equation. So below we have a bunch of equations that are going to relate our equilibrium, which is our K constant, electrochem, our E naught at standard state, so that's our voltage, remember, and thermochem, delta G for Gibbs free energy. So you have a bunch of equations that are all finally summarized for you right here, depending on if you're going from equilibrium to electrochem, thermo to equilibrium, etc. So you have all that as a resource for you right there. Remember, Q is not at equilibrium, and K is when you're at equilibrium. And these are both products over reactants always. Okay, so let's go ahead and take a look at this through the lens of an example. So we're going to consider our Danielle cell here, our zinc copper cell. So our zinc copper cell, let me zoom in for you just a bit. And that's when we have our zinc metal placed in 1 mole of zinc nitrate solution, and then we have copper metal as our other electrode placed in a 1 molar copper nitrate solution. And this is at 25 degrees Celsius, so of course that's standard state. Write the balanced overall reaction for this process, including E cell. So I'm going to give you just a moment to pause the video and write that. And remember, you get those values, the reduction potentials, from right here, from this sheet. And that is the table of standard reduction potentials. Okay, go ahead and pause the video and then come back to check your work. All right, welcome back. So I'm going to start with my anode half reaction. My anode is my zinc solid being oxidized. So zinc 2 plus 2 electrons. My potential, my standard oxidation potential is the opposite of my standard reduction potential that I looked up on my page. So I'm going to have to flip the sign here. So this is plus 0.76 volts. And my cathode, where reduction is happening, is Cu2 plus 2 electrons going to Cu copper metal. And my standard reduction potential was just what I read off the sheet, plus 0.34 volts. Now remember, I compared my zinc and my copper. I saw that zinc was negative 0.76, copper was positive 0.34, so I chose copper for my cathode because it's more easily reduced. Just a quick little review from the first section there. So my overall reaction includes everything except for the electrons. So notice I'm already balanced here. I have the number of electrons given off as taken in. So my N is going to be equal to 2 in this case. I'm just going to write that as a note for myself right now. N equals 2 because I have 2 electrons transferred. So my overall reaction is zinc in the solid state plus copper ions, and that's going to yield zinc ions plus solid copper. And my overall cell potential equals positive 1.10 volts. Now that means that our cell is spontaneous in the forward direction there, and that's our voltage if we were to measure it in the wire. Now what are the values of delta G naught and KEQ for this reaction? So for delta G naught, I can look at my previous page and I can figure out, okay, which equation do I need to use? So I want to figure out delta G. Delta G naught is equal to negative NE times F times E naught. So I've already figured out my E naught. That was 1.10 volts, the standard cell potential. So now I'm just going to plug everything in. So delta G naught equals negative N to E negative. So the number of moles of electrons times F times our cell potential. And plugging everything in, I already said my N is equal to 2. And so that's 2 moles of electrons that are transferred per this entire reaction. So I'm going to plug in my negative sign, don't forget that there. And then I'm going to use a lot of parentheses so I can keep everything separate, especially for canceling units here. So 2 moles of electrons for each 1 mole of my reaction. My F, my Faradays, are 96,485 coulombs over 1 mole of electrons. 1.10, and I'm looking at my E cell right here, which is what I figured out above, 1.10 joules per coulomb, which is a definition of a volt, joules per coulomb. I'm putting that in here so I can cancel out my coulombs. Plugging all of this in, well first actually, let's go ahead and cancel our units. So I have my joules going away. Oh, sorry, not going away. Keeping my joules. Sorry about that. I got overly ambitious about canceling units there. Okay, meant to say my coulombs are going away, my moles of electrons going away, and now I have joules per mole of reaction. So my final answer, when I plug this into my calculator, should be negative because I have my negative sign here. So that ends up being negative 212,267 joules per mole. And an easier way to write this is in kilojoules, right? Because that's a huge number. And that's equal to negative 212 kilojoules per mole. Okay, so that's my delta G naught. Let's figure out my KEQ. So my KEQ equation is going to require me to find E naught first. To find K. So what I'm going to do is I'm going to go ahead and rearrange an equation. So we're going to start here. So E naught equals RT over NEF ln K. So you can find that equation again on the first page. So rearranging this, multiplying both sides by NEF. So E NEF over our RT, because that's still on the bottom, equals natural log of K. And to get rid of this natural log, I'm going to use base E. So E to the E naught and EF over RT is going to equal K. So now that we're at this point, I'd like you to pause the video and try to figure out what K is. So plug in all of the values that you have and come up with an answer for K, and then come back and check your work. Okay, welcome back. See what I did there? You're finding K, and I said okay. No, I'm just kidding. Okay, so K equals E to the, now our E naught is what we found up here, 1.10 volts. So that's going to be 1.10 joules per coulomb, which is the same thing as a volt. We had 2 moles of electrons, that's my N. Faraday's constant, 96,485 coulombs per mole of electrons over R times T. R is our ideal gas constant, so 8.314 joules over mole times Kelvin, and 298 Kelvin, because we said we're at 25 degrees Celsius. So add that to 273 to get your Kelvin temperatures here. So when you plug all of this in, all your units are going to cancel out nicely to be able to give you K. So you're going to end up getting 1.62 times 10 to the 37. And that's our KEQ there. So we can see that KEQ is very, very positive. And that lines up with our positive E potential, or potential cell voltage up here. So that means we're going to go in the forward direction. Okay, so this was all at standard state. Let's see what happens now if we change some of the conditions. So instead, if we had zinc at 0.1 molar and copper at 0.5 molar, remember before they were 1-to-1 ratios there, 1 mole and 1 mole. Instead now, say we have 0.1 molar and 0.5 molar copper, how does the voltage change? Explain by using the magnitude of Q, and then finally, how does delta G compare to delta G naught? Okay, so the first thing I want to remind you of is at standard state. At standard state, Q is equal to 1. That means the ratio is going to be the same. So in our first example where we had 1-to-1 products over reactants, our Q is equal to 1 there. Of course, our E will be equal to E naught, and our delta G is equal to delta G naught, right? And that's just to tell us that we're at standard state. So let's figure out what our Q is. So Q is going to be products over reactants, and if I look at my equation that I wrote above, my product is going to be zinc 2+, my reactant is going to be copper 2+, and we're dealing with the ions here as given, so zinc 2+ over copper 2+. So Q equals my concentration of zinc ions over my concentration of copper ions, and then just plugging in those numbers that are given to me in this problem right here. That's 0.10 over 0.50. Of course, 1/5 is 20%, so we can just do that without a calculator. 0.20 is our Q. Now, this Q is less than 1. So since Q is less than 1, that means the reaction right now is to the left of standard state. So it's going to proceed in the forward direction. So E is going to be greater than E naught in this case, and G is going to be greater than G naught. So our Q is less than 1. Remember, 1 is at equilibrium. If we're less than 1, we're left of standard state. So the reaction is left of standard state. And that also means that our E, our potential, our voltage, is going to be greater than the voltage at standard state. So we're going to have more volts now, not at standard state, than we did. That means we're going to expect a number that's greater than 1.10 volts. And our Gibbs free energy is going to be less than the Gibbs free energy at standard state. That means it's going to be even more negative, so it's going to be more favored to go forward. Okay, last part, part D. Let's see if we were right. Calculate the values of E and delta G, because we said we think they're going to be greater with the initial concentrations given in part C, so the non-standard state example. Let's go ahead and calculate those. Actually, I'd like you to go ahead and pause the video and see if you can calculate both of those, including finding the equations on your own, and then come back and check your work. Okay, welcome back. Let's start with delta G. So delta G equals delta G naught plus RT ln Q. Our delta G naught was negative 212 kilojoules per mole. And where did I find that number? Right here. We calculated it in part B at standard state, our delta G naught. Negative 212 kilojoules per mole. Okay, so delta G plus RT times ln Q. So plus our R's are, of course, our ideal gas constant, 8.314 joules over moles times Kelvin. And I'm going to need to get this into kilojoules to match my kilojoules over here, so I'll just go ahead and convert that in line. So 1 kilojoule is equal to 1,000 joules. RT, of course, in Kelvin temperatures, we didn't see any change in temperature given here, so we're still going to assume 25 degrees Celsius, unless told otherwise, which is 298 Kelvin, times the natural log of Q, and we figured out what Q was already up here at these same conditions, so 0.2, ln 0.20. Okay, plugging all of this in, we get negative 216 kilojoules per mole. Okay, so is that greater? Is this greater as we expected before? Or I'm sorry, not greater. Is this less than? Is the magnitude, the negative magnitude higher, I meant to say. So is this more negative than delta G naught? Well, yeah, if we look up here, it was 212 kilojoules per mole. Now when we're not at standard state anymore and we have a different number of products and reactants there, our delta G is going to be more negative. That means it's going to be more spontaneous in the forward direction. Okay, let's do the second part. Let's do E, the electric potential there. So E equals E naught minus RT over NEF times ln Q. Okay, going ahead and plugging this in, we calculated E naught, that's at the very beginning up here, 1.10 volts. So I'm going to go ahead and plug that in, equals 1.10 volts minus, and then plugging in my ideal gas constant, do a lot of parentheses, keep things straight, 8.314 joules over moles times Kelvin, times 298 kelvins, again, that same temperature we're assuming. My number of moles of electrons hasn't changed, same reaction, so 2 moles of electrons times Faraday's constant, 96,485 coulombs, times the natural log of 0.20, because of course we figured out our Q already before. So when you plug all of this in, you get a value of 1.12 volts. So is this what we expected? So is the cell potential greater than the standard cell potential? Well, we had 1.12 out of the non-standard state and 1.10 volts at standard state. So yes, that is absolutely a higher voltage at non-standard state. Okay, so that is it for you for the whole lesson 7.2. There's, of course, only this one video for it. Thank you for your attention. Bye.